Hello and welcome to this aerospace testing webinar, which is being held in partnership with United Electronic Industries. The webinar is called Standards-Based Avionics Testing in a Post-Pandemic World, Remote Distributed Testing. I'm Ben Sampson, editor of Aerospace Testing International magazine. First of all, thank you for joining us. So today we're going to talk about remote and virtual bench testing and various standards and how those standards are evolving to help test engineers do their jobs better. But it won't be me speaking today. We're lucky to have presenting for us two representatives from UEI. First off, I'd like to introduce Christian Herbepin, who is Avionics Systems Business Director and Technology Advisor from UEI. Chris has worked for 38 years in ground and flight testing, starting with the software development of avionics benches, working with the company that eventually became Airbus Helicopters. In the 1980s, he did in fact join Airbus. Then by 2012, he was nominated Airbus Group's Test Methods and Tools Executive Expert. In 2017, he was made the group's test domain roadmap owner. During recent years, his efforts to promote the ED247 standard have led his colleagues to name him Vista's Evangelist. He joined UEI in April 2021. Joining him today is Erik Goethert, who is Senior Director, Business Development and Strategic Marketing at United Electronic Industries. Erik designs, manages, and implements projects that collect real-world data for the aerospace and defence sector, something he has done for more than 30 years. So just before I hand over to Christian and Erik to give their presentation, I'd just like to remind everyone, please do submit questions during the talk while they're giving their presentation. You can do that via the box on the right-hand side of the screen that you should see via the Q&A box. Don't hold back. Feel free to answer them. You won't see them instantly, but when we are in the Q&A session afterwards, they will be published as I ask them. So, Christian, thanks for joining us again. Please start.
Thank you for this introduction. During this webinar, we will go through different aspects of the avionics ground testing. The context and challenges, the benefit linked to the usage of standards, and as example, the presentation of two protocols. One is the Vista's protocol, called also ED247, and the IDDS one. And finally, we will enter in the Q&A session. As it can be probably confirmed by people around this virtual table, an important part of the avionics benches are in fact based on proprietary solutions. The bench configuration, control, and display software is quite often the result of an internal development. Hardware vendors have proprietary interfaces, most of the time based on drivers available only for a limited number of operating systems. The development, maintenance, and obsolescence management of such systems is costly and not really obvious. For integration benches, the resources needed are most of the time dedicated and collocated in the same area. The I/O equipment are generally centralized in acquisition base, which imply a complex and expensive wiring solution. Switching from virtual component to the real one is not obvious, and it's more and more often needed. The way to monitor data coming from virtual or real equipment are not done in the same way. It means that you have to redevelop some scenario depending on the fact that you are using real or virtual equipment. Unfortunately, despite some improvement, silos are still existing between the simulation and the test domain. And last point is we can notice that during the last year, the part of the virtual testing is increasing a lot in order to reduce the cost. This point can probably also be confirmed by the people around the table. In all organizations, the pressure on the test cost cycle is increasing. So it becomes absolutely mandatory to reduce the cost and delay linked to the bench design, realization, and validation to secure the in-time availability of the ground test resources many months before the flight. It's really a pity when these resources are not available in time. Find a way to reuse and share more efficiently hardware and software resources. Very often, these resources are duplicated or redeveloped. Realize test, and especially the integration one, as early as possible in the development cycle. As you know, it's less costly when you detect issues at the beginning. It's also mandatory to improve the efficiency of the test process itself, to reduce the delay, and to increase the test coverage. The new target is not only to get the certification, but also to improve the maturity of the product. It's also needed to take benefit of the new organizations and technologies like the extended enterprise and the cloud computing. In this period of COVID crisis, it could be also very useful if we can do and control the test remotely. And last point, but not least, is to mitigate the impact of the obsolescence issues which occur more and more quickly. I remember when I started my career, it was the normal way to still use the same equipment during more than 10 years. Today, this time is completely over. So, why do we need to standardize? The key point is to minimize the acquisition, implementation, usage cost, but also to reduce the delay. So the fact to have a standard available has some impact. You have many vendors of the instrument. So the fact that there is many vendors stimulates the different vendors, offer to the user a large choice with some complementary offer, and it's also a way to mitigate the obsolescence issues. The fact to have many buyers of the system push the vendor to develop more efficient equipment, and it has also a positive effect due to the scale to the cost. And it allows also a better interoperability between the different entities, internal or even external. The fact that the standard is developed by a working group has also some benefit. It produces for me an architecture more robust. The implementation is more reliable by the fact it reduces the risk. But also the fact that the same bricks are shared between different usage, it reduces the maintenance cost, and it's also a good opportunity to have some innovative ideas coming from the different members of the group. And it facilitates the application extension, because when you develop internally, you develop based on the actual requirement. And sometimes when you have new requirement, it's not easy to extend. If you have a standard, it's based on the requirement coming from different entities, and it creates some opportunities. Last but not least is the fact that most of the standards introduce some abstraction layers. So the fact that some bricks are already available reduces the development effort. It brings the compatibility with multiple hardware through the hardware abstraction layer, and also the compatibility with different operating systems. It's also a way to have a common language when you discuss between different entities. Most of the time, the standard introduces its own definition of the different elements, and it's also a good way to reduce the learning curve. So as example, we will present two of the standards used now in the frame of avionics testing. The first one is EV247, which is called also Vista. This standard is defined by the EuroCAE, the European organization leader in the development of worldwide standards for aviation. So the EuroCAE Workgroup 97 is in charge from this standard. It started his work in 2013. The first of the standard was published in, we will see a little bit later, in 2017. The initial objective of this standard was to facilitate the full simulation, allowing a way to share virtual components between all the different aerospace industry actors, aircraft manufacturers, or avionics equipment providers. But in addition to these initial objectives, the new one is to reuse the standard in order to reduce the realization, delay, and acquisition and usage cost of the test benches, especially the hybrid one, mixing real and virtual components, but also all the training simulators. This is possible adding in the working group some hardware and software test component suppliers and also some training manufacturers. So just a brief view. I don't want to enter in the detail, but you see the working group members are coming from the aeronautic aircraft manufacturer, but also equipment manufacturer and test hardware or software providers. So if you are interested to join this group, do not hesitate to enter in contact with the chairman of this group, Olivier Fourcade, at Airbus. At the end of the presentation, you will have a recap of all the resources and links available. This standard is mainly based on the virtualization of all types of signal we can encounter on an aircraft. It could be analog, voltage, current, LVDT, temperature, stress measurement, or discrete of different kind, but also, of course, all the avionic buses like the Airline 429, the serial line, the CAN bus, the IDDS, and the MIL bus. But also, now it's needed to introduce voice and video. This virtualization is done by digitalizing and timestamping multiplexing on an Ethernet bus with the following constraints. And this constraint is clearly one of the main differences between this standard and other existing ones. The first is to minimize as far as possible the latency introduced by the virtualization, as the target is to be able to use the standard not only for the development, but also for the certification. Limiting the second one is to limit the CPU, memory, and bandwidth usage. And it's really a key point if we want to achieve the first one. Last one is to reproduce with a very high accuracy the timing and counter on the original line. So this is the history. So the work started in 2013, and the first release was published in 2017, including the IDDS, rank, canvas, discrete, analog, and non-avionic data. The release A was published in 2020, and it's improved some part of the non-avionic data, and it introduced new type of signals like the serial line, the voice, the video, and the metas. End of last year, the work started in order to prepare the release B of the standard. Mainly the target is to introduce control and command, instrumentation, virtual component delivery format, and adding additional transport protocol. The use cases. In fact, the ED247 is usable on both sides of the V development cycle. On the left side for the full simulation, on a single computer, or if needed on multiple computers, or even in for the virtual massive testing using the cloud. Because clearly, in order to ensure the certification and the maturity of the product, the number of scenarios we have to test is increasing a lot, and using such solution is a good way to do more test coverage. On the right side of the V, it could be used for unit testing or for integration testing at different level, at functional one, or even for the complete aircraft. But it can be used also for the development of training simulators, reusing some of the model developed during the previous phases. And my dream is also to be able to use this for the maintenance. The idea is if we can have some avionic equipment delivering the data in the frame of the standard, in order to do the maintenance of the aircraft, you will need just a laptop. So, what is the high-level architecture? You have two buses. One, which is called the virtual avionic buses, is the one used to transfer the data coming from the virtualization. So this data can be directly sent to the virtual component. Okay? Or if you are in a hybrid test bench, you have to use an I/O bridge in order to transform the virtual signal to the real one in both directions. The second bus, called the supervisory one, is mainly used to send command to do health monitoring and configure the system. As you can see, the different tools have to be connected to both or to only one. I don't want to enter too much in the detail of the structure of the packet, but just to give you an appetizer, the current release is based on UDP. So you have the normal UDP packet, and the UDP payload is based on an optional Vista's header and the Vista's payload itself. The Vista's header contains the component identifier and a sequence number. This sequence number is used to detect any packet loss. And in the header, the last part is what we call the transport timestamp. Is the timestamping done when the packet is pushed on the network. In terms of channel, from the beginning, from the release dash, we have the data packet linked to a channel. This contains the timestamp, But this time, it's not the transport timestamp, it's the acquisition timestamp. For example, for an arrange line, is the timestamp of the first bit of the 32-bit word on the bus, and after you have the data itself. In the some of these fields are not mandatory. All the fields in the purple are optional. The point that we have introduced in the release A is the capability to have a multi-channel packet, which is in fact the way to multiplex different channels together in order to limit the number of sockets. As you can imagine, when you have to simulate, to virtualize a complete aircraft, you have thousands and thousands channels. So it's not very efficient if you have to open this number of sockets. So there is a way to multiplex in the same packet data coming from different channels. So of course, a small header, additional header must appear, identifying the channel and the size of the packet. So what are the standard benefits? It provides an ultra-light, and I insist on this point, ultra-light way to virtualize the exchange between the different components. It's also provide the capability to log and replay the exchange between the equipment, respecting accurately their timing. And this is a key point if you want to achieve to the certification with using the standard. The IO abstraction layer provided by the standard make the software developed independent of the hardware and the operating system. This point allows to share and reuse models all along the development phases, even if the environment is completely different. For example, to reuse them for the development of training simulators. It's very efficient for hybrid testing because it's really easy to mix real and virtual equipment during the same test and to swap very quickly some real equipment to virtual one or vice versa without having to change anything in the wiring. It offers also the possibility to do distributed testing. It means that all the components under the test are not needed to be co-located. It also allows the fact that we can do very early the integration test, even if some components are still located at the provider facilities. Last point, but not least, is the fact that now, if you use completely the standard, the connection between equipment, avionic equipment, is not anymore a bunch of wiring, but just an Ethernet cable. So it produces a drastic reduction and simplification of the wiring. And the idea is to put the bridge mentioned previously close to the real component in order to minimize this wiring, which has a big impact on the design cycle and, of course, the cost. So, a brief introduction of what we call the resolver concept. If you want to virtualize a complete equipment, it means that you will have hundreds of components. So each component definition is provided in an XML file called ECD for ED247 component definition. So the process consists to give to the resolver all this definition of equipment and to provide also some IT constraint. For example, if you cannot use the multicast in your environment, or if you can use only with a limited number of IP address. You can define this, and you can define also some user preferences. And the resolver will provide the configuration files that will have to be loaded in the component. So it produces what we call the instance configuration file, ECIC. If some error or issue are detected, the resolver will also inform the user of the conflicts. For example, if two different components are unfortunately allocated with the same IP address, it will be detected. But also, if some resources, or if some source are missing, if one component uses an arrange line, and if this arrange line is not produced by any other component present in the test, you will have a message. So once more, if you have a small bench, it could be done manually. If you want to virtualize a complete aircraft, you have to develop a software acting as the resolver. So how do we configure the I/O bridges? It's done through two different files. One, the ECIC, as explained previously, which describe all the network aspects. Okay, and this format and the associated schema are provided in the standard. The second one is the one describing the hardware configuration, like the pin connection, the gain, the offset if needed. These two files are used by the bridge during the boot phase in order to configure the bridge. When you present this standard, most of the people ask the question about the latency. So in order to have a concrete answer, during the last months, a lot of tests have been done, and I will just present two of them. For the analog and the discrete, we have this configuration with a signal generator sending its output to an I/O bridge and simultaneously to an oscilloscope. The acquisition bridge transfers the Vista's packet to the replay one, okay, and this replay one rebuilt the analog signal and send it to the oscilloscope. By this way, we can measure the latency between the initial signal and the virtual one with a very good accuracy. For the arrange, it's a little bit more complex. So, for example, we can use an inertial unit sending the message to the acquisition bridge. This bridge sends the SNet packet to the replay one. The replay rebuilt the line and send it to the first acquisition bridge. So by this way, you can timestamp both signals, the initial one and the reproduced one. As we can move the inertial unit during the test, it's quite easy spying the packet sent by the bridge to measure the latency. And what we have noticed is, in both cases, the measured latency was below 2 milliseconds for a local network. Of course, if you have this bridge in Europe and this one in US, the latency will not be anymore 2 milliseconds. It will be below 100 milliseconds. So it's a key point. Depending on the test you have to do, is the delay introduced by the virtualization is compatible with the test you want to do or not? Is the first question you have to answer before starting to build the architecture of the bench. So, what are the ongoing improvements? As mentioned briefly previously, the idea of the work started end of last year is to bring some clarification, because we have received some questions from people that has used the release A of the standard, to extend the functionality and to add some better implementation solution to bring performance, but keeping in mind that we need to have a very good backward compatibility. In order to realize this, in order to be more efficient, it has been decided to split the work in 3 subgroups. One subgroup for instrumentation, the second subgroup for command and control, and the third one for all the other topics. So the subgroup instrumentation target is to define a generic protocol allowing to, of course, monitor data exchange between the components, but also to access to the data, internal data of the component, in the case of the component is a real one or a virtual one. Second point is to realize failure injection and value overriding with the same application to the data exchange between the components, but also to the internal variable of the component, real or virtual. The main idea of this concept is, if you have developed a scenario, exactly the same scenario could be used if you have real or virtual equipment. So it means that you have to develop an abstraction layer for these actions. For the failure injection and the value overriding, you can decide if you want to apply this at the source level. In this case, all the consumer will be affected by the failure injection, or if you want to apply this only to one of the consumer of the data. The subgroup command and control will have to formalize the way to load and start the virtual components, to define clearly what is the state machine, to provide a list of command and control and the mechanism to use this, a health monitoring system in order for the bench supervisor to know exactly in real time what is the status of the bench, and to manage the time, covering the real-time simulation, or if you have no real equipment in the loop, you can run the simulation at the maximum speed, or you can run the simulation step by step for debug purpose. Of course, this last point is like the previous one, only usable if you have no real equipment in the loop. The third group will update the mailbus standard, already present in the Rev A, but probably we will do some evolution to introduce new types of avionics signal. For example, we have a request for the paneling bus, which is a military bus used not by all the aircraft manufacturers, but at least by the military one, to add new transport protocol, as mentioned, to improve the performances. So we have few candidates like IDDS, TGM, TSM, shared memory, and RDMA. We will see later in the next slide more information about the RDMA. Next point is to standardize the format of the delivery of the virtual component, okay, in order to ensure that the effort to integrate a component developed by someone else is extremely limited. Last point, to be honest, I don't know if it will be done for the release B, is to define a standard conformity assessment process. Okay. Once more, if you are interested to contribute, feel free to contact Olivier. So now I want to give you more detail about one of my favorite candidates for the transport protocol. This transport protocol will not replace the existing UDP1. It will come in addition. And this protocol is the ROCKY 2 transport protocol, which is part of the RDMA. So the main targeted benefit of this protocol is to reduce drastically the latency. We will see how in the next slide. To reduce not only the latency, but also the jitter latency, to limit the resources used, mainly by the CPU, but not only. As mentioned previously, it's also a way to use better the bandwidth. To reduce the packet loss. The current release is based on UDP, and as you know probably, when you send a UDP packet, you are not 100% sure that all the consumer will receive it. So this is a point that could be improved. This protocol offers, as UDP, the possibility to have multicast message transfer. And one advantage of this one compared to other candidates is it's an efficient usage of existing network infrastructure. You don't need to change all your network or your switch. The idea is to be able to reuse with this new protocol all the existing infrastructure, even with a wide area network. So the ROCKY standard is not something invented by the ED247 working group. It's already used in many application areas, like the cloud computing, the enterprise data server, the big data, and the most important one is the high frequency trading used by the financial guys. And as you can imagine, these guys have in mind to reduce as much as possible the latency, because latency means a lot of money. As you can see in the bottom of this slide, this protocol has already been adopted by key players in the IT world, like Cisco, Microsoft, IBM, and other people like NVIDIA. So how does it work? If you have a transfer through the UDP, as you can see in this animation, the application buffer is transferred to the different layer of the system, and each time it's include a copy of the buffer and usage of the CPU. So it takes time, and depending on the load of your system, you can have a big jitter around the latency. With the RDMA, the idea is to have a direct transfer from the application layer directly to the network interface card in both directions. Like this way, you have no additional copy, and the operating system or CPU are not involved in the transfer, just in the initialization of the transfer, but not during the transfer itself. So there is different RDMA, but as mentioned previously, for me, ROCKY is the most adaptive one. It's developed on the Ethernet standard, over the Ethernet standard. It's compatible with 1, 10, 40, and 100 gigabit per second on copper or fiber. It's built on the top of UDP IPv4 or IPv6 on the link itself. And in order to make it lossless, in conjunction of, you can implement some standard like the 802.1qBB in order to have a flow control mechanism in place, or the 802.1qAZ, giving you the opportunity to reserve some bandwidth for a specific class of traffic. And the last one is 802.1qAU for managing the congestion mechanism from end to end. If you apply these two, if you implement these two additional protocols, which is mainly taken in account by switch like the Cisco one, you are not far to have a lossless technology. So here, just to illustrate what could be the implementation of ED247 with Rocky inside the new UAI CPU based on the Zinc FPGA. The Zinc FPGA is based internally on 4 ARM core at 1.5 GHz, 2 core at 600 MHz, and a Mali core at 667 MHz. So if you look what can be done, okay, you see, and the key point is the ARM core are only involved for the configuration, command and control, but the real-time transfer is done without any involvement of the core or from the operating system. So the latency is reduced to the minimum. So in this case, we can reduce drastically the latency introduced by the virtualization. So, as conclusion, the 3 key points you have to remember from this presentation is: point 1, after years of work and meeting involving key aeronautic players, the ED247 achieved now with Wave A a maturity level compatible with operational implementation. Point 2, the Wave B will be published Q2 next year, and it will bring additional functionality like the virtual component control and command, access to internal variable of the virtual or real component, error injection, and value overriding. And I hope standardization of the virtual component delivery format. Performance improvement, especially in terms of latency, thanks to the reduction of the new transport and introduced by the new transport protocol and an adapted hardware. Of course, UAI will contribute to the development of the standard and be a key player in this development. Now I give the floor to Erik.
Gosh, thanks, Chris. So now on to another standard, one for engine test. We see many of the same issues there. Can you advance the slide, Chris, for me?
Yeah.
So what's the problem here? Well, let's look at it adding a new piece of instrumentation to a test system. Most hardware vendors have a proprietary interface protocol. They advertise it as open because they publish the details of that protocol. The software driver is often available from the vendor. However, the integration is different from all the other operating systems and the different programming languages, and it may not support a real-time OS. You heard this from Chris before, I believe. This driver may or may not be suitable, which may result in writing it from scratch. As you well know, this work can be costly to perform. Again, exactly what Chris pointed out. Steps include writing the test procedure, testing, integration into the product verification cycle, and more. Okay, so let's say the new system can communicate. It still needs to be configured. So what are the options and where do you set them? How do you prepare and change preset configurations? And we shall mention the size and the environmental suitability. Where do you plug it in? Are there enough spare slots? What if it needs to be located close to the engine or a unit under test? Is it backwards compatible, or shall we say incompatible? And of course, the target system would have to support the legacy hardware and interfaces and also new devices that meet the new standard. So why IDDS? What does it offer the measurement community? Well, you've heard this before, so here it is again, reduce costs. So how does that happen? Reducing costs. Well, by the reduction of integration time. Technologies like the OMG DDS or data distribution service, a publish and subscribe framework based on a common interface definition language, both for the data acquisition control and data path interfaces. This technology will reduce the integration time and provide portability of measurement devices across different data acquisition system suppliers. Devices conforming to the standard become basically driverless. And it solves a common interface challenge in an open format. The new standard defines the way in which measured data and configuration and control information will be packetized and exchanged on the data bus. Sounds very similar to Vistas, I believe. It also bakes in legacy support. Note that the instrument data path interface is not limited to a DDS. That is, the control path interface can set up a device to stream data in any format supported by the instrument. However, the working group has standardized on the OMG DDS data path application protocol for the instruments. That is the basis of IDDS. But wait, let's not forget the last bonus. Another big value of IDDS is timestamping at the source of the data. Using another standard, IEEE 1588 or PTP, Precision Time Protocol. This allows for the distribution of network-based instruments throughout the test environment, closer to the unit under test. This timestamping of the data at the measurement source enables reliable time-based cause and effect analysis of complex coupled systems. Now let's list some of the discrete benefits to the various stakeholders in the IDDS world. Let's start with the user. An IDDS compliant system can receive new compliant hardware without the need to develop or purchase new software. This also means that the measurement system is easily scalable and can grow or shrink as required. Since the system is not tied to a particular vendor, large portions of the system can be upgraded or changed with competing suppliers. Users can buy new instruments with new capability or improved performance without having to involve the original system supplier. Since IDDS utilizes a common data standard, this will allow customers and third parties to write special or custom applications, say for a specialized data visualization or analysis tool. These tools increase productivity internally and can be easily sold to others, kind of like an application store. And then the instrument vendor. They can sell directly to the instrument users, as the hardware does not need to be integrated by a system vendor. Any specialized tools or software can be commoditized. And then, of course, the system provider has a broader choice in measurement hardware, selecting the best value for the customer. This lowers the cost to add new instruments to their portfolio. So here are some of the goals for an IDDS-based system. Well, the first one is to make them plug and play. The devices will self-identify to the network using a hello world message. The device's model is then used to configure and control the device and allow for diagnosis and recovery. Self-configuring editors based on a textual data model and not a hard-coded GUI. This model-based approach extends beyond the instruments to the system itself. Again, the model describes the configuration and control parameters for all instruments. System editors can self-configure from the model. The addition of new devices to the system does not require code development, compiling, and testing. There is now an added capability to render a command line interface, a web UI, and a programmatic interface, all from that model. System validation and rollback are also supported. Metadata associated with the system changes is systematically recorded in the model-based hierarchy, allowing for rigorous validation and rollback if needed. IDDS also strives to make troubleshooting easier with better error reporting. Using a global standard as the standard for state management of the system objects allows an overall hierarchical system tree view to be programmed, allowing a user to drill down to find a problem node or individual problem measurement channel. A simple color code system is used: green for operational healthy, yellow for somewhat degraded, and red for failed. Users can right-click to recover or reboot a node, to take it offline, and even to swap it with another device if it is not recoverable. The use of industry standards for both the control and data interfaces provides a solid basis from which the developers can work. Many open standards are used that constitute IDDS. On the control interface side, we use Yang models. Yang allows the configuration and control structure of all elements of the system, most importantly, the instruments, to be described. This enables simple programmatic or script-based access to instruments and other system elements for configuration and control. The global standard from CCITT recommendation X.731 to define state management, and of course, IEEE 1588 PTP for network clock synchronization. All of this using a publish subscribe middleware or data distribution service. On the data side, sharing data amongst all the devices, publishers and subscribers, is accomplished with a data distribution service. OMG DDS is well recognized with commercial and open middleware versions are available. Many of the vendors, as well as the open source version, have all been used on both the instruments as well as the viewers and controllers. Other data interfaces are still supported on the system network to be connected to a non-IDDS device. Sorry, next slide. So this is a little bit about IEEE 1588, or Precision Time Protocol, that is used to synchronize the clocks in the system. This is ideal for networked systems since no new cabling is required, as it is using the existing Ethernet connections. A grandmaster clock keeps all the clocks synchronized, while boundary clocks at the switches compensate for any network latency and keep their local instruments synchronized. With an accuracy of plus and minus 300 nanoseconds, all samples can be timestamped at the point of acquisition. However, it is up to each instrument to actually utilize this in its hardware. Here's a pretty good system diagram. All the data is available on the IDDS network. In the past, sharing data to remote subscribers has been difficult. Well, as we all had to discover in the past 2 years in this pandemic, using a system such as IDDS allows remote viewing and even control to happen, keeping not only the people safe, but also the test article. Here's a list of companies that currently have team members around the IDDS working group table. They represent some of the biggest names in the aerospace and aero engines around the world. UEI are proud to be founding members along with MDS and Rolls-Royce. So what have you learned from all this talk and all of these slides? Well, I'm seeing a trend in these two standards. Can you go back a slide, please? I'm seeing a trend in these two standards, even though one is for avionics and one is for engine test. They both strive for reducing costs by minimizing the development and validation effort of these systems. So it is worth reviewing these points. With many vendors of instruments, all agreeing on a common driver or hardware abstraction layer, all working together with the final customers and integrators, a better system can be developed. So the future of testing is here, pushing down the costs, solving interface challenges, and reducing integration time. These are common themes with both Vistas and IDDS. Whether it is using existing open standards, adopting changes, or inventing new ones, it is helping transform design, testing, and verification tasks in this post-pandemic world. Here are some of the resource links added that are there for Vistas as well as IDDS, and we certainly welcome all of your input.
Thank you, Erik.
Open it up to a couple questions quickly.
Yeah, good idea, Erik. Yeah, thanks. Thank you for both of you for interesting presentations there. I find it fascinating the changes going on at the moment with the digitalization of avionics and how standards are changing to take advantage of all of those benefits. Are you guys okay to take a few of these questions now? We're squeezing a few in. I'm thinking yes. So I'll just crack on. So this one here, first one here is from Sergey Kolganov. He's asking if you can tell him about the tools that are used to prepare ECD XML files. He says the manually transferring data from Excel ICDs to other XML tables is a potential source of mistakes. So what do you do in case of ICD modifications?
So, in fact, the standard describes the schema of the file, of the XML file, but there is in the standard nothing describing the way to implement the generation of these files. It means that it can be done manually. Of course, if you have a complete aircraft to describe, if you have to describe all the components, but as the component can come from different entities, and there is at the moment no standard to describe the ICD, each entity has to define the process. But clearly, of course, it's better if this is not done manually.
Anything to add there, Erik, or I'm guessing not? No. Okay. How about this one from Thomas Buell? I'll ask you that first. So he'd like to know about non-local routing, Christian. Do packets take different paths and arrive out of their transmission order in that situation?
So, of course, this situation can happen. It's why in the structure of the packet, you have a serial counter, incremented by 1 at each packet transfer. So, and you have the timestamp. So by this, you can resynchronize and detect some misordering in the packet transmission. It's why it is the usage of this counter.
Okay, thank you. And then finally, 2 questions here from Steve Dame. Steve, thank you for these questions. The first one, he wants to know what are the cloud vendor requirements that are needed to implement the ED247 virtualization standard in terms of network, the performance of the network, the constraints, and the location.
So I think AirDMA could be a solution because it's something which is already used by the cloud actually for a different purpose. But to be honest, this has not been tested yet, and it will be a part of the selection of the candidate for the release B. So if you have some specific requirement or information on the topic, you are more than welcome in the working group.
Okay, and the second question from Steve. Are ED247 virtualization tool stacks compatible with the RTCA DO330 tool qualification standards?
I cannot say yes. This work has not been done, and we are working now with the authority in order to ensure that at the end of the story, the tests done through the standard are compatible with the certification process. But this has to be demonstrated now.
Okay, all right. Thank you very much, Christian. I can't see any more questions coming up, so I'll just offer Erik an opportunity just to make any concluding remarks. He can, if he wants now.
Well, thank you so much, and I thank everybody for attending, and I certainly thank Aerospace Testing International for hosting and Chris for his knowledge.
Yes, thanks, guys. And just a final note to everybody that's tuned in today. The recording and the presentation are available afterwards. Everybody that's registered will receive an email with a link that gives them access. And then eventually it will be posted on the aerospace-testing-international.com website. Oh, and also for more information, this is a bit of a shameless plug, but the latest issue of Aerospace Testing has an article which is almost exclusively Christian talking about distributed testing. So if you want to learn more, that resource is also available online. Okay,
just one point.
Yes.
If you have additional questions, feel free to send emails. Huh? I will do my best to answer, and I'm sure that Erik will do the same.
Cool. Definitely. All right. Thank you again, guys, and thanks everyone for tuning in. Have a great day. Enjoy the rest of your day. Cheers. Bye-bye.
Okay, bye.